Right, this video is for all those who want to do a quick review on Taylor Maclaurin and the Lagrange Error Bound, which is the last unit of AP Calc BC. All right, let's get started. If you need this PDF, by the way, just let me know in the comment section. And the exact sum of the series. Okay, what does this look like? To me, it just looks like the Maclaurin of e raised to x, that series when x is 3, because we know that e raised to x is given by 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. And if I just replace x by 3, I'm going to get 1 plus 3. Obviously, 1 factorial is just 1, although I can put a 1 factorial, but it's not going to make any difference. 3 square over 2 factorial, 3 cube over 3 factorial, and so on. So the answer that we are looking for is e cube for the first question. All right, over here, find the power series of this center at x equal to 7. Give the first 4 non-zero terms and a general term. Okay, this reminds me of 1 over 1 minus x, because the power series of 1 over 1 minus x is 1 plus x square plus x cube and so on, which is obviously centered at x equal to 0. Agenda in this question is just to manipulate this somehow to make it look like this. I know that the center is at 7, so I want negative x minus 7 somehow, right? So that's why I'm going to subtract 7 and add 7 in x, because that's mathematically allowed. I can do that. And then I'm going to open this up. So 3 is x minus 7 is now taken as a unit. So it will become 3 times x minus 7. And then 7 times 3 is 21. So it will become 21, and minus 20 is as it is. So this will look like 12 over 21 minus 20 is 1. So 1 comes here, plus 3 times x minus 7. That's what we have. Um, uh, Almost same, right? Almost same. Obviously, the first term just became 12, or 12 can be taken outside as a common factor. It doesn't really matter. Or I just need this as a negative sign. So that's not a problem, because I can rewrite this as 1 minus and minus 3x minus 7. That's how I can manipulate this. So this looks like the general, I think the function manipulated, and it's what do you call it, as the power series is going to look like 12 is just taken outside as a common factor. And now I'm going to write the first 4 terms. So that first 4 non-zero, that's what they want, right? So it will be 1 plus, I will say x, so x means this entire thing, so that x is negative 3x minus 7. The next thing is plus negative 3x minus 7 whole square, and then plus I would say negative 3x minus 7 whole cube, and then plus negative 3x minus 7 raised to 4. Obviously, we can decorate this if you want to. So this will become 1 minus 3 times x minus 7. Negative 3 square is 9. 9 times x minus 7 square. Negative 27 x minus 7 whole cube. And then what, plus, I think, 81 x minus 7 raised to 4. So that's how it's going to look like. And they want a general term as well. So for example, for here, the general term is given by the summation is given, the sum is given by summation of x raised to n, where n goes from 0 to infinity. So this is the general form. So in our case, the general form is going to be 12 remains as it is. New x is negative 3x minus 7, and that is raised to n. That is the general form, which can definitely be decorated a little bit as negative 1 raised to n taken out, and 12 times 3 times x minus 7 raised to n. So this is going to be our general term for this question. Right, over here we have to write a first for non-zero and general term of the Taylor series of f about x equals 0, which is basically the Maclaurin series. I'm just gonna use the same concept of 1 over 1 minus x is given by 1 plus x square plus x cube and so on. So using that, I can rewrite 1 over 1 plus x square as 1 over 1 minus of x square, and the Maclaurin of that will be given by 1 plus, this is a sort of our new x, right? So 1 plus negative x square, which is basically replacing x, plus negative x square, which is for this term, then negative x square cube, which is the next term. We need first non-zero to four non-zero. These are the first four. So I'm going to go for this. That's going to look like 1 minus x square plus x to the 4 minus x to the 6. But this is not the end, because there is still a 2x over here. So I'm just going to multiply 2x on both the sides. So it's going to look like 2x over 1 plus x square will be equal to, so 2x is basically multiplied here, so it will look like 2x minus 2x cubed, because 2x times x squared is 2x cubed, plus 2x raised to, I think, 5, and then this will be 2x raised to 7. So I think this should be our this should be our first four non-zero, and the general term will be, so it's better to find the general term of this one, which is going to look like, I think, negative x square raised to n. And this general term over here, our final answer, that's going to look like 2x times negative x square raised to n, which can be written as 2x times negative 1 raised to n times x raised to 2n, which can also be written as negative 1 raised to n times 2x raised to 2n plus 1, because x raised to 2n and x will become x raised to 2n plus 1. This 2 is as it is, and negative 1 raised to n is just negative 1 raised to n. So that's our answer, right? Right, now next, the derivative of ln 1 plus x squared is this. Find the first four non-zero terms of the Taylor series of this about this point. So I'm just going to borrow my reserve from here, because I know that 2x over 1 plus x squared is 2x minus 2x cubed plus 2x raised to 5 minus 2x raised to 7. And if the derivative of this is this, then it makes sense that the integral of this is this, right? So I'm just going to integrate both the sides with respect to x. So I'm going to put an integration dx, integration dx. So this is clearly ln of 1 plus x squared. And this, when integrated, 2x when integrated, will become x squared. This will become 2x raised to 4 over 4. This will become 2x raised to 6 over 6. This will become 2x raised to 8 over 8. Don't forget the constant of integral. So it's going to look like ln of 1 plus x squared is going to be x squared minus x raised to 4 over 2 plus x raised to 6 over 3 minus x raised to 8 over 4 plus c. Now to find c, we can just say that for the function fx is equal to ln 1 plus x squared, we know that if we put x as 0, f of 0 will be ln 1, and ln 1 is also 0, right? So we can just use x equal to 0 and basically 0 comma 0 as a point. So replacing the left side with 0 and the right side with 0, 0, 0, 0. So 0 plus c. So c is just 0. So the answer is basically the same thing with c replaced with 0. So the answer is x squared minus, that doesn't look like a square, x squared minus x to the 4 over 2 plus x to the 6 over 3 minus x to the 8 over 4. I think that should be our answer. Right, Lagrange error bound. This one is about Lagrange error bound. So P3x be a third degree Maclaurin polynomial of f using the information from the graph. Y is equal to, okay, this graph is of fourth derivative of the function, all right? Show that this is less than 1 over 400. And if you look at it carefully, this absolute value, so P3 1 over 4 and f of 1 over 4. F is the actual function, right? And P is the approximation of this. So this is basically the error, right? We are looking for the maximum value of error, in other words, which is obviously the Lagrange error bound. So we know that the maximum error is given by absolute value of the maximum value of the fourth derivative of the function at some value z over 4 factorial. Why fourth derivative? Because it is a third degree Maclaurin. That's where we are approximating to. So that's why this will become 4, this will become 4 factorial, and this will become x minus c raised to 4 as well. Okay, now maximum value of, and by the way, what is z? Z is between 0 and, I'm sorry, z is between x and c over here. Okay, so fourth derivative of function over 4 factorial is, I think, 24. X is 1 over 4, and the c is 0 because that's a Maclaurin. So Maclaurin is centered at 0. So this is 0 raised to 4 over here. Now, we know that we are already given the graph of, the function, right? The fourth derivative of the function, an absolute value. Sorry, this should not be x to c, by the way. This should be c to x, because c is already 0. It makes sense that it should be c to x. Okay, now between 0 and 1 over 4, 0 is right here and 1 over 4 is this, because this is 1/2, this is 3/4, and this is 1. So between 0 and 1 over 4, what is the maximum value of the absolute value of this function that we are looking for? Isn't that just this, which is 15? So can I replace this with 15? This is 24, and this is 1 over 4 raised to 4, right? If you do this using a calculator, actually, you know what? I don't know if calculator is allowed or not. I think it is not. So let's try to simplify this manually. 3 5s are 15, 3 8s are 24, and this is 4 raised to 4, which is, I think, 16 times 16, I would say. So this one simplified further, I think. Okay, we need to somehow make the comparison between these two, right? That these two actually matches. That's what we are looking for. So since I need a 400, right? I need to compare this somehow with 1 over 400. I'm just gonna multiply this with, so this is by the way 256. I'm just gonna multiply with 400 and divide by 400 because I want to somehow manipulate this in that form, right? So this 1 over 400 is taken out because that's what, after all, we want to compare with. And the remaining terms, as in 5 times 400 over 8 times 256, remains as it is. 8 times 5 is 40 and 0. So this becomes 1 over 400 times 250 over, sorry, yeah, 250 over 256. Now this makes perfect sense, because if the maximum error is this, and don't you think this number is less than 1? So this number is already less than 1 over 400. I'm not sure if that makes sense. I can help you with the numbers if you want using a calculator so that you understand. 250 over 256 is 0.97. So this is 0.97 over 400. And don't you think this is less than 1 over 400, because 0.97 is just increased to 1. So that's what we need to prove, and that's how we need to prove that after this point, I'm just going to say that this is also less than 1 over 400, which is exactly what we wanted to prove, that the maximum error is less than 1 over 400. Right, the next one is the function has a continuous derivatives for all x and da da da. Right, a third degree polynomial at about x equal to 3. That's pretty straightforward, right? I'm just going to say that the third degree polynomial is going to look like f of 3, about 3, is f of 3 plus f prime 3 x minus 3 about x equal to 3, right? Yeah, yeah. Then we have f double prime 3 over 3 factorial x minus 3 square. This is second degree, and the third degree will be f triple prime 3 over, sorry, this will not be 3 factorial. This is 2 f double prime. So this is 2 factorial, and this is 3 factorial x minus 3 whole cube. And we now have the values. F3 is 5, f prime 3 is 2 times x minus 3, f triple prime 3 is negative 4 over 2, because 2 factorial is just 2, and then f triple prime is 7 over 3 factorial is 6, x minus 3 whole cube. So this is the approximate value. Make sure to place a squiggly symbol over here. that fx is approximately this. And now you want to approximate what, f of 3.2. So this is definitely calculator active. All you have to do is replace 3.2 over here. I'm pretty sure you can do this. I'm just gonna write the expression over here. 7 over 6, 3.2 minus 3 whole cube, and that's our answer, right? All right. Lagrange. Forced derivative satisfies this inequality. Use this information to find a bound for the error in the approximation found in A. So they are looking for error. We know that the error maximum value is given by absolute value of maximum of fourth derivative of the function at some point z over 4 factorial. Why am I doing fourth derivative? Because it's a third degree Taylor polynomial, so error always takes one more than that number. And then x minus c raised to 4 is going to look like. Now what is the maximum value? And what yes, of course, z is between c and x. I know that x is 3. That's what we are finding this about. I'm sorry, x is 3.2 because that's the approximation, and the center is 3. So between 3 and 3.2, we can clearly see that the maximum value is 35. So I'm just going to replace that max with 35. 4 factorial is 24. X is 3.2. This is 3 already, and this is raised to 4. So this should be our maximum error bound, which is, if we need a decimal, this is 0.00233. That's what we have over here. Find an interval so that this lies. So basically, they need a range for the approximation. So for that, first we need the sum, actually, this number that we just left. So I'll just find that quickly. This is coming as 5.3293. Now the range looks something like f of 3.2 is less than equal to the approximate value of the polynomial that we got at 3.2 minus the remainder, the third remainder, as an R3, as in what we have as the remainder at that point, which is basically the error, again at 3.2, and then over here P3 3.2 plus R3 3.2. What is this number? 5.3293. So 5.3293 minus 0.00233 less than equal to f of 3.2 and less than equal to 5.3293 plus 0.00233. That looks something like this after the calculation. Can f of 3.2 be equal to 5.329, 5.32, well, 5.326 and 5.33. So 5.329 is in between these two, right? So I'll say yes, it can definitely be equal because it is within this range. Using the Maclaurin of cos, right, is the fourth degree of this approximate da. Okay, so we know that the cos Maclaurin looks like 1 minus x square over 2 factorial plus x raised to 4 over 4 factorial, and I will stop here because they need fourth degree. So the approximate value of m4 of x is, I'm sorry, not m4 of x, because this is already m4 of x, by the way. It's not cos, so I will say that this is fourth degree Maclaurin, and this approximate this value. So I'm gonna write, I mean, officially I'm gonna say that cos of pi over 12 is approximately m4 pi over 12 is equal to 1 minus pi over 12 whole square over 2 plus pi over 12 raised to 4 over 4 factorial. I wrote 2 because 2 factorial is just 2, right? So let me calculate that. Right. Oh my God, who asks 7 decimals? Seriously? 7 decimals is going to look like 0.9659262. How many? 1, 2, 3, 4, 5, 6. Okay. 6 to, oh my God, that's 3. Okay. Oh, well, okay. All right. Last question, use the Lagrange error bound to show that this is less than. So that's the same strategy, right? We're going to use the same strategy that this is the error, and I know that then the error value is going to look like maximum value of the, this is the what? The fourth degree, right? So maximum value of the fifth derivative at z over 5 over 5 factorial times x minus c raised to 5 over here. What is the fifth derivative of cos? Honestly, I don't care because it's either sine or minus sine or cos or minus cos, right? Whatever it is, its maximum value. I know that z is between what, c and x, and c is what? This is Maclaurin, right? So c is 0, and the x value that we are trying to find is pi over 12. Now you might think that we cannot just take the maximum of whether that's sine or cosine as 1, because we have to restrict ourselves in this restriction. That's true, but you're actually just going to take it as 1, honestly, because APs are always going to give you questions like this where eventually you have to take this as 1. So you can disregard this restriction actually. So like I said, this will be 1. 5 factorial is 120, and x is pi over 12, correct? Pi, that's what we are trying to approximate, and c is just 0 raised to 5. So this is going to look like equal to pi raised to 5 over 120 times 12 raised to 5. And this approximate value comes out as 1.0249 times 10 raised to minus 5, and 1 over 5,000 to compare. That's going to look like 0. Actually, I can just write this as, well, 2 times 10 raised to negative 4. So obviously this is a bigger number, right? So if I say that the maximum error is this, I can also say that this number is also less than this number over here. So in a way, I can say that the error, after all, error is equal to pi raised to 5 over 120 times 12 raised to 5, and this number is already less than 1 over 5,000. So the error is less than 1 over 5,000. That's how we're going to do it. Hope that makes sense.